Bismillahirrahmanirrahim. Hi, hope everybody is doing okay. Today we will be looking at hypothesis testing. This is a very interesting part of learning statistics because we are going to connect the descriptive statistics and inferential statistics. Yeah. In Malaysia, as a background, there are a lot of interest in complementary healthcare treatment. Yeah. So, for example, from studies done in 2013, was shown that among diabetes patients, Malay and Muslim are more likely to use traditional and complementary medicine compared to other ethnic and religious group. And this finding was also repeated in another study in specifically in Pahang. Yeah. And at schools, unfortunately, there has been peddlers of complementary treatment for different purposes. Yeah, people gain access to children at school to conduct mass bath therapy to treat attitude problem, learning disabilities, and so on. And in fact, if you search for the products on the internet, you may find something like this with a very big claim that therapy oil and so bath therapy set can cure or can provide a cure for autism, ADHD, hyperactivity, and other learning disorder. Yeah. So, can we test whether the claim is true? What evidence do we need to collect to support this this claim? Yeah. And would one test be sufficient to make a strong conclusion about the effectiveness? Yeah. So in this with this in mind, we want to look at how we can conduct hypothesis testing to answer questions that we may have about what's going on in the real world. Yeah. Or the questions that we have about research. And let us consider this contemporary question. Yeah, with vaccines for COVID-19 entering the market, people may be asked, how much would you be willing to pay to get COVID-19 vaccination? So let's say one person said, my answer is 100 ringgit. And then the government declared that the price for the vaccine is 1,000 ringgit. So do you think this person will buy the vaccine? Perhaps not, because that person had already stated he is willing to pay up to 100 ringgit and not more than that. However, if the same vaccine actually costs 10 ringgit, do you think that person will buy the vaccine? Of course, yes, because that person had set an even higher ceiling price. Yeah, so 10 ringgit is much cheaper than the 100 ringgit that this person had set in his mind to buy a COVID-19 vaccine. Yeah, so we can see that when we want to accept or reject something, in this case the decision to buy COVID-19 vaccine, we need to refer to our acceptance and rejection criteria. The same way with statistical testing. Yeah, when we have a score, for example, a score of Q, which is one standard deviation away from the mean, would we consider that the score is near to the mean? Or in other words, is Q considered a common score? And compare that to R, which is 3 standard deviation away from the mean. Would you also accept that the score is near to the mean? It's quite likely that we would be willing to accept the alternative idea that R is actually far from the mean. Yeah, and this is why we need to specify a threshold for acceptance and rejection before a test is conducted. We cannot move the threshold based on the result that we get. And this is why we need to know and also understand the area under the curve, yeah, which is usually expressed in terms of percentage, because this information can tell us how common or how rare is a score. And we'll mention a bit more about this later. Yeah, but for now, let's look at how we can come up with research hypothesis based on research question. So in this example, the research question is bath therapy effective to cure learning disability? This is quite a big question. And to answer this question, we need to do the following at the very least. First, define what are bath therapy and learning disability. We need to have conceptual definitions of bath therapy and learning disability. So the examples of the definitions are given in the slide. And then we need to state how bath therapy and learning disability will be measured. Because a bath is a bath, but maybe a bath therapy need to fulfill certain requirements. So we need, for example, to have a checklist to see how well the procedure was applied during the bathing process. Yeah, for one bath to be considered a bath therapy. Yeah, so we have a measurement criteria, and for dyslexia, maybe we can measure using correctness and also the speed in spelling and reading task. And then this would constitute our operational definitions. After we have determined the operational definitions, we need to determine the population and sample. So for this example, let's say the population are children between age to 12 with a diagnosis of dyslexia by a clinician. And the sample would be children who fulfill or who are in the population, but they are specifically in special education classes from 2 schools. So these are the children in our study. And then we need to outline the method to test the effect of bath therapy. What kind of research method that we want to use. For this example, we'll say that we are going to use a pre and post design where the children will undergo bath therapy, and we will measure the dyslexia score before the therapy and also 1 month after the therapy. Yeah, and from this set of information, the definitions, the population, sample, and also the method, we can come up with our research hypothesis. We have 2 types of hypothesis, null and alternative hypothesis. Null hypothesis is normally written as H0 or H0. So in this example, the null hypothesis is dyslexia score is the same before and after the therapy. Null hypothesis, is usually a hypothesis with no difference or no effect, or it reflects the status quo. The alternative hypothesis, in contrast, says that there are differences or there are effects of a treatment. So in this example, we have H1, dyslexia score is lower after the therapy. Yeah, and notice that we have a hypothesis where the score is determined in one direction. Yeah, or the score is predicted to be in one direction, not determined. Yeah, the score is considered lower for the therapy to be effective. If the score is in fact higher, that means the therapy is effective at making dyslexia even worse, and this is not what we want. Yeah, okay. And the steps for hypothesis testing itself. First, we state the hypothesis, and we have mentioned about the null and alternative hypothesis. And then we set the rejection threshold or the type 1 error, and the typical threshold is set at 0.05 or 5%. And for more serious or critical decisions, we may want to have lower type 1 error. Type 1 error, it means rejecting a null hypothesis when it is actually true. Yeah, so we want to keep this at a minimum. For example, for COVID-19 vaccine, we want to know or we want to test whether the vaccine is effective in treated and also untreated sample. So we would use a much lower threshold, yeah, because we want to minimize type 1 error. And then we organize the data. If we don't have the data, we need to collect the data, and we can organize the data in our statistical analysis software, clean the data, and then recode if necessary, and then we run the analysis. We don't have to calculate the test statistics ourselves. Usually this will be produced by our statistics analysis software like SPSS, JAVS, or Jamovi. Yeah, but on our side, we need to look out for the test statistics, degrees of freedom, and also the p-value associated with that test statistics. If you are keen on doing inferential statistics, you will find test statistics like T, F, and chi-square. Yeah, and then we compare the obtained p-value against the alpha. Is the p-value smaller or bigger than alpha? And once we have determined the relative size of the p-value compared to the alpha value, then we make a decision. Yeah, we either reject or accept the null hypothesis. And some people say if we accept the null hypothesis, it means we fail to reject the null hypothesis. And then a little bit more advanced information here. We can calculate the statistical power associated with each statistical test, but that's for a different video. Yeah, so let's go through another example to determine whether a score is considered common or rare. How big a score can be before it is considered significantly different from the mean? Of course, a score which is not exactly the mean is different from the mean. But how big does it has to be different to be considered a significant difference? Scores located in 95% of the areas under the curve would typically be considered common or high probability scores. Yeah, remember that I've said alpha is commonly set at 5%. And so this is why 95% of the area under the curve is considered common, yeah, areas for common scores. And scores located in 5% of the tail, in this case the tail is on the right side of the distribution, they are typically considered rare or low probability scores. Yeah, and this is another one tail test, but then we are looking on the negative side or on the left side. How small a score can be before it is considered significantly different from the mean. So the score that fall in the 5% area would be considered rare or low probability score. So we may reject the idea that they are the same as the rest of the population or the rest of the distribution. And then we have a two-tail test. In this case, we are asking how big or small a score can be before it is considered significantly different from the mean. So a score can be either too high or too low. Or in other words, a score can be either too big or too small. And they would be considered significantly different from the mean. Just like before, 95% of the area in the middle of the distribution would have the high probability or common score. And the scores in each of the tail on the right side and on the left side would be considered rare. And this time we have 2.5% because we have two tails. If we add those values up, 2.5 plus 2.5, then we will have 5%. Yeah. Okay, now let's consider this example with a null hypothesis that dyslexia score is the same before and after the therapy. and we set alpha equal to 0.05. And based on our data, we find that the mean of dyslexia score for the group of students is 25 and the standard deviation is 5. And after the treatment, the score is, let me correct this, is 20 and standard deviation is 5. And we find from the output of our statistical analysis software that the p-value is less than 0.001. So is this bigger or smaller than alpha? It is smaller. 1% is smaller than, 1% is smaller than, it's not 1%, it's 0.1% is smaller than 5%. Yeah. Okay, so because the obtained p-value is smaller than the alpha, yeah, we reject null hypothesis. We can say that the score, the dyslexia score after the therapy is smaller after the bath therapy. Yeah, but this is a hypothetical example, a fictional example, just to demonstrate the idea. You can do your own experiment, you can do your own study to test whether products that claim to cure learning disability is in fact able to cure learning disability. Just a question for you to ponder. Do you think this is a one-tail test or a two-tail test? What is the alternative hypothesis? And before we go, let me show you this example. We have a distribution of score before and after the treatment. The blue distribution is the distribution of scores before the treatment. And we have two situations over here, perhaps from two different studies. In one study, the mean of score after the treatment is higher than before, but the distribution are overlapping quite a bit. In another case, which is on the right side of the diagram, we have the distribution of scores after the treatment to be very different or have very little overlap with the distribution of scores before the treatment. In which study or for which diagram are we more willing to accept that there is a true difference of the mean for before and after a treatment? I think if you have understood the presentation so far, you would be able to answer this question. For more, please look at other videos that will follow this, inshallah. And if you have any question, leave your question in the comment section. You can also like and subscribe to this channel. Thank you very much. I'll see you again.